G'day Internet and welcome to River City Ransom Underground. My name is Andrew Russell. I'm the lead programmer on River City Ransom Underground, and in this series I'll talk about some of the technical features in the River City Ransom Underground engine. Now, you will remember that last episode we left off, we were looking at this diagram. Oops, there we go. And basically, I was talking about how we divided the level up in how we divided levels up into sectors. So I had a level, and I would drop it into here, and these are all the sectors for my usual testing level that you've seen many times before. So, and then we talked about where's the painting? Okay. We talked about how we divided the level up into sectors using basically a kind of flood fill that's sort of specifically designed to flood fill out regions, considering what you can walk sort of to and from. And we talked about sort of all the reasons we did that. So we end up with these sectors. And the important thing to sort of realize with these sectors is that it's not the sectors that we do the navigation on. The way we do the navigation in the game is that we navigate on edges. So let me just draw that in. This is going to make my gorgeous diagram even more gorgeous. So we're going to say that there's an edge there. So clearly let's use green. I'll run out of colors. So there's an edge here, and there's an edge here, 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 and that's it. That's the total number of edges in the level. So when we want to go from, let's say, sector A over here, where our smiley guy is, he's extra smiley now. We want to go over to point C, so we're going to go over here. So for instance, we might say to get to there, we need to go sector A to D to C, which I've just scribbled over the letter C, but it's here. So to do that, we need to go through an edge here. So that's that edge there, and that's that edge there. So we need to go somehow from here to the edge, to the next edge, and then we get to our goal. And we know that between these edges, as we were saying before, this is freely navigatable space. So because they're convex, you can go from any point to any other point in there without running into one of the walls. Whereas if they were concave, you could, cross across these walls. That one there and that one there, you could run into them. But we know that our sectors are convex because we made them that way. So all we have to do when we're navigating is considering the edges, and then finally this goal, what we do to do that in game is we make basically a fake edge. So we basically have A to D to C to goal. So we know that if we just drive towards this becomes like a queue. So we just drive towards this edge here. So basically these are that one, that one, that one. So if we just drive towards these edges, so that being I'll draw it in blue to make it clear that is this fake edge here, is this one there. So if we just drive towards those edges, we will get there. So once we get here, once we reach this edge, we can say, right, we've done that. Once we reach that edge, we'll say, right, we've done that. Once we reach that edge, we'll say, right, we've done the entire path. So we can just keep crossing them off. And as we drive through, we just always go towards the first one that we haven't crossed off yet. So we'll cross that off, and then we start going towards that one until we reach it, and we cross that off, until we reach that one, and we cross that off. So that's the process for getting between from one point to the other in the game. And I say edge because it's an edge in sort of a graph theory kind of way as well. So let me up the production values. As we know in this series, doing this always results in havoc. So I'm just going to do a semi-transparent layer here. So what we end up with is we have nodes in a graph. So we have node A, B, C, D, and I call that one Q, and node R. And these are linked by edges, like edges in the sort of geometry sense, but also edges in the graph theory sense. So we have an edge that links these two nodes. We have an edge. I'm going to say that that doesn't actually intersect. So we'll say we have an edge that links these two nodes. We have an edge that links those two. We have one that links those two. And one that links those two. And then finally one that links these two. So if you can sort of find a path through this graph, say you want to go from sector A to B to C, you can get to basically any destination on the map. So you might be in D, you might go A, R, Q if you wanted to get to Q, for instance. So, and then as I said in the previous episode, we use an algorithm called A star to actually do this pathfinding. And I'm not going to go into too much detail on how that works. Suffice to say, it's a very fast way to find paths through a graph that are the shortest path through a graph in an efficient way. You use an algorithm called A star. And last week I pointed out that there's this excellent article, Introduction to A star, on the Red Blob Games website with interactive diagrams. So it shows you all this process. It shows you, it explains that you've got nodes and edges in the graph and you combine them. So I'm not going to go into too much detail about how A star actually works because I can just point you at this article and say, just read this because it's great, and you can, play with the diagrams, which I absolutely love. So, so let's have a look at some actual pathfinding happening. Recalling, that we get it going between sectors, but we're making our path out of edges. So we start, that's the one I wanted. We start here with here we go. And you'll see, if I turn them on and off, you can see that there are actually edges in here. And one thing I already realized that I've kind of glossed over is the fact that when we say we have an edge that's bidirectional here, we actually have one edge here and one edge there. And that distinction will become important later on, but we'll just say for now that if you've got a double-headed arrow, we actually have two separate edges, one to go one direction, one to go the other direction. Okay, so let's have a little watch of this guy. I'll zoom in on him. So here's Glenn, and he's sitting on a chair. It just happened to be a simple sprite that was available sort of early in the development process when I was working on this particular bit of prototyping. And if I click him somewhere, you'll see he makes a path and he starts following it. And you see the edge highlights go away, and it actually highlights the edges that he's going to walk through. And we'll talk about that probably in a later episode, exactly what those highlights mean. But suffice to say, he's picking edges to walk through and going there. And so, and if I put him in, say, here, he can navigate his way around this level to there, and he can get back up into that corner, and he can, change paths halfway through and go there. He can, navigate something like a long path like this spiral that goes through several sectors. And, here's another spiral that spirals in the opposite direction. We can go back the other way. So, let's see, what else have we got? So I wanted to show, let me just find the file. So you remember last week that I dropped some other maps onto this prototype application, and I said that this one is one of the pathfinding sort of stress tests, because this makes quite a large level with very long paths it has to make its way through. So a lot of time was spent basically driving this character around and figuring out sort of all the edge cases that could happen and what weightings and stuff needed to be put into the A-star algorithm to basically make nice paths that sort of looked reasonable, and so it wouldn't get snagged on anything, and it wouldn't hug the walls and stuff. And we'll talk about some of that in later episodes. So, I'm going to show this maze because it's kind of cool. I can put our little Glen up the top there, and I can click on the very end of the maze, and you'll see that he immediately finds a path through this maze. So what I want to talk about just quickly now is that obviously, we want the pathfinding to be as fast as possible. We are running a game, and the game runs at 60 FPS. That's 16.666 recurring milliseconds per frame. And so on one frame you might have let's say we've got a guy, he's a bad guy, so he's going to be in red, and we have a good guy and he's going to be in blue, and we might have a path that goes to get to here, and then all of a sudden the guy in the blue might die or disconnect or something, and so the AI has to go and pick another guy to find a different path to go to. And this needs to happen in 60 frames per second, or much less. Great drawing there. Much less than 16.6 frames per second. Milliseconds. It has to happen in a much smaller amount of time, because you could have several enemies needing to pathfind at a particular point. So, so the point of all that is that our pathfinding has to be fast. So let's talk about some of the optimizations we do. So you can see found a path after considering 71 nodes, visited 73, deleted 0, skipped 0, queued 0, walked back 69, total path cost. That's the how expensive the path is. So that's not an actual optimization. That's just how long the final path will take to walk. But let's put this map back on, because this one's probably a bit easier to show these things. So let's say, for example, we have a guy here and we want to walk him there. So I'll zoom in. He's up here and we want to walk him here. And to do that, we have to search, and we see the walkbacks is 2, visited 5 nodes. And so what we're trying to do is we're trying to, as much as possible, reduce the number of nodes in the graph that we search through. So you can see here that we have 1, 2, 3, 4, 5, 6 nodes. If we're just going from A to C, it'd be really great if we never had to look at those nodes, and we just looked at nodes that are sort of vaguely in the right direction, because as I showed last week, one of the main benefits of A star is it reduces, so here's Dijkstra's algorithm, it has to check pretty much every node that it could possibly get to within that distance, whereas A star is smart enough to realize it can check just a small subset of nodes. But if we can reduce that even further, we save a lot of time. And one of the ways to reduce that is if we accurately estimate distances. So one way we do that is for every node in the graph, we estimate how far away it is from a so for every sector and for every edge, actually, and I think we only store the edges in the end, but we actually calculate it for both for various reasons. We store the distance, so we actually know from this edge how far away this red sector here is. I'm gonna so I'm just checking what I want to talk about. Yep. So what we want to do is, if we're going here, let me pause. There we go. if we're going to the red sector here, we know that we don't really need to consider this green sector up here, and we don't need to consider this yellow sector here, because we know that this sector, if we're going to the red sector, is actually further away than the blue sector. So let me take a screenshot and just sort of demonstrate that with some actual numbers, just sort of to make it really clear. So we're going towards the red sector. Just get my pen. So the distance here might be 100, and the distance in the red sector is 0, and the distance here might be, say, 40, and the distance here might be, say, 60. The distance here is pretty much going to be the same as that. This might be 100, and this might be 80, let's say. And so we know we're at 100, we want to go down to here, and we're now at distance 60. We know that we don't want to check into this sector or into this sector, because that's just taking us away from our destination. We actually, 80 is greater than 60. So we know that this path we don't follow and this path we don't follow. But this one is less than 60, so we go there, and then we finally go here. And so that's one of the ways that we avoid spending too much time looking at other sectors. And so, as you can see, there's a whole lot of different numbers here. I'm not going to go into too much detail about what they all mean, because it took a while to sort of sit down and figure out the most optimal thing to do, because obviously it might be a thing that spends too much time or storage actually doing the optimization, so you have to make sure you're always reducing the number of operations the computer has to do and the amount of memory it uses. But suffice to say that a lot of work is going into making this search as fast as possible, so that we can search across large maps without having any sort of frame hiccups. So anyway, the other thing that I want to talk about is that each of these edges can store extra information. So it could just be, the edge might just be a walk edge, where you walk from one place to another. But we can also tag, we can tag these edges, and this is why it's important that, you can go between two things, there's actually two edges, one going one way and one going the other way, because they might have different tags. So we can have a walk edge. We can also have a jump. Spelling, getting ahead of myself. Jump edge. Or the opposite of that is a drop edge. So, we might have A and B. And if that was a ledge, we might jump on one direction, and to go back the other way, we have to drop to go the other direction. Let me see. So there's a couple of other edge types we have. We have climb edge. So in cases where there's like a ladder connecting, like here's a sector and here's a sector, we need to let the AI know that to get from A to B, he's got to climb this ladder to get to there. So that and that, and we've got an edge here that says that is climb. And then finally, let's make I think I can scribble it onto here, just fit it. We have what's known as a jump edge. So we might have a level, and I'll draw it out. What we have is a long jump. How do I misspell jump twice in this dream? It's talking and writing at the same time. So we might have like a little pit that's filled with deadly spikes, and we don't want to go in there. But we have a guy here, and he wants to get to here. So what we do is in the level editor, because we don't want them jumping all willy-nilly, we actually place down a a jump point. And so this is semi-automated. You only have to draw in the start of the long jumps, and the editor, when it builds up, when it builds up this thing, when it builds up the sector map and all of the other, and when it builds up the sector map, it then goes and generates all of the edges. And as it generates edges, it will look for little jump points that you put in the level, and it will say, right, well, we'll test all the different ways we can jump from here. So we can do like a short jump, which might end you up in the pit, or we could do like a running jump, which gets you across there, and that gets you there. It might also say, here's a short jump here. Let me see if I can pan this image across. I have run out of space on the canvas, but it might say that short jump there doesn't get you anywhere. So that's all in the one sector here. So that's useless. So this might be sector Q, and so we'll call that one Q, and this one R, and this might be sector R. And so we know that we don't want to generate an edge going back here because it's pretty useless. So, that's never going to be useful to anyone, but it's a long jump edge. But this one from Q to R, long jump, we actually do want to generate. So as long as we give the editor, as long as we tell the level where the interesting places to jump are, it will go ahead and it will try out all of the different possible jumps, so a short jump or a running jump, and see if it lands in a different sector, and if it gets somewhere interesting. And obviously, as you saw, let's see if I still have it up. Levels. There we go. So as you saw, this level, you can get sectors. I'm going to screenshot this and sort of show it. So edit, paste as new image. And I'll do the same thing too, so I can scribble on it quite nicely. So say we put a jump point here. This will probably explain this a little better. Say we put a long jump point here. What will happen is it will go and say, right, we can jump there, we can jump back here, we can jump back here, we can jump back here. And it will say, right, well here is somewhere that we can only get to by dropping down, running across and jumping. So it will say, store that one. It will look at this one here. It will look at this one here, and we'll say it's the same sector, so don't bother. No. Make sure we're in different colors. I'll get rid of that one. And it will also look at the ones here and here, and it will say, oh, those are going to places that we can just walk, so there's no point in jumping there. So it'll also get rid of those ones. So in the end, it just stores this one edge here, and that will be a long jump. So finally, after explaining all of that, oh yes, and then one last thing is you can also tag an edge with run. So that gives us a running long jump if we combine those two tags. But you can also have a running jump and a running drop and a run climb, or just a running walk edge. So I don't think we generate any of those, but in theory it's possible. So the AI will sort of say that if it wants to get from A to D, it better run if we tag that with run. We don't actually do that, but it's a thing we could do because the AI supports it, because it just understands the concept of running through an edge. So with all of that being said, let's actually look at it in game. Now I've got a different level up here because this lets me show off all the different edge types. So first of all, let's just have a look at the sectors. So you can see there, if I flatten it out, there's the flat mode, and you can see here this is the 3D mode. So this blue sector is projected upwards. So again, this blue sector. When I say blue, I mean this purple sector here. You know, if I do that, it's pushed upwards if I put it out of flat mode into 3D mode. So the reason I'm on this level and I've got Glenn rather than Alex is because I have, let's turn off the sector map, I have my little navigator bot, and he happens to be on Alex. And let me send that full screen. So what I can do with this is I can click Alex around, and basically this does exactly what I was saying is the main point of this, and that is we can pick anywhere in the level, and you know, if we need to be there for, say, combat, say we need to be here to fight Glenn. Oops, I just killed him. Let's make a new one. You know, if I need to be here to fight Glenn, you know, I can just say, put me there. And the navigation system will figure out everything it needs to do to get from point A to point B. So he could be all the way across here. If he wants to be go and fight Glenn, he will just walk straight there. So the reason I brought up this level in particular rather than the usual one, the courtyard one that I normally use, is because this has examples of all of the different edge types in the one sort of space. So first of all, there's a jump edge. So in between the two sectors here, in between this yellow sector and this pink sector, there will be an edge that says jump. So I can, I can stand there and I can jump up there. And to go from the pink sector to the other one, there's also an edge that says drop, and that just gives it permission to drop down. So normally the AI will avoid dropping if it doesn't expect to drop, just as a way to avoid sort of falling off cliffs. But if it expects to drop, because there's a drop edge, it will do just that. So, that is a thing that it does. What other types we had? We had a climb edge. So here's a climbing surface, and so I can come here and I can say, climb up here for me. And he knows to do that, and he gets a bit tired at the top of a climb, but that's all right. And I can do sort of complicated route finding. So I can go from here, I'm going to come on top of the boxes, and now, so that wasn't as complicated as I thought, because he could drop down there. So let's show that going the other way, because obviously he can't jump that distance. He can drop it, but he can't jump it, so he has to come up like back in the diagram. What's happened here is we have a case where we have a drop edge, but we don't have a jump edge because the jump height is too high. So that's another. I love this level for showing this off because it's actually great. Let's bring up that again. So yeah, so he can drop down there, but he can't jump up there, so he has to jump across there or across there. He could, in theory, climb up there, but he'll probably decide that the shortest route is to jump up to there and jump up to there. But to get down, he just drops. So he knows that that's the fastest way to get down. And then finally, as I said, I've gone in and I've stuck a, and I'll probably keep this because it's actually a good idea. I've stuck a long jump I've stuck a jump marker down here in the editor, and I've stuck one down here. And so he knows that if he wants to get across that gap, he can just do a long jump. And we haven't been through and necessarily tagged all of the levels where they need long jump points, but we've sort of got the important ones where they would fall into spikes otherwise, or just refuse to go because they can't get between A and B. But there's a few places where it's nice to just be able to jump directly between two points like that. And so yes, so I can jump there. So finally, let's climb him all the way up there. So he's going to drop down because he's decided that's the fastest way, and the fastest way to get up there is from there. But to get down here, fastest way is to drop. To get up here, the fastest way is to climb. So I can't actually. It's a bit interesting because I can't directly predict what he's going to do because the algorithm will figure out what the fastest way is, and what we try and do is make it seem like the sort of path that a human would take. But sometimes it's like the computer says, well, no, human, you're actually dumb. It's actually faster to go this other way. But most of the time we do a pretty good job. So let's see. Let's look at my notes. I think that's everything that I had to show you. Let me turn off the navigation map just so you can see this just in all its glory, because I know that I've just been demonstrating that with the sector map up. So, we can go between these two places. We can jump up here, we can walk over here, we can drop down here, we can climb up here. You'll notice he sort of goes a little to the side so he gets to the climbing zone. We can come down here, walk onto this thing, we'll jump up onto this box and do a nice long jump across between these boxes. And we might come down here and fight Glenn, or we might just walk off into the sunset or the other way. So that is everything that I had to show you for this episode. In the next episode, we'll talk a little bit more about how we're generating these paths and stuff like that. So thank you again for watching, and must always remember to do this. You can visit my blog at andrewrussell.net. You can follow me on Twitter at _AndrewRussell. You can subscribe to me on YouTube, where you're probably already watching this video, so you'll get notifications on all of these three places when I put up new videos. You can also follow the game on Twitter at River City Ransom and on Facebook at River City Ransom Game, and both of these accounts will be retweeting and reposting my videos as well. So that's it for this video. Thank you very much for watching, and I will see you next time.